Welcome back to our final series of videos in our ongoing lecture on relational databases. This set of videos will be addressing the issues of normalization. In this series of lectures on normalization, we discuss some of the theory that's been developed with the goal of evaluating relational schemas for design quality or design goodness. That is, to measure formally why one set of groupings of attributes into relation schemas is better than another. The bulk of this series will be on informal design guidelines for relation schemas. We're going to cover functional dependencies, normal forms based on primary keys, and general definitions of second and third normal forms. Then we will touch briefly on Boyce-Codd normal form, multi-valued dependency in fourth normal form, and join dependencies in fifth normal form. So let's proceed. There are two levels at which we can discuss the quality or the goodness of relation schemas. The first is the logical or conceptual level, how users interpret the relation schemas and the meaning of their attributes. Having good relation schemas at this level enables users to understand clearly the meaning of the data in the relations and therefore to formulate their queries correctly. The second is the implementation or physical storage level, how the tuples in a base relation are stored and updated. This level applies only to schemas of base relations which will be physically stored as files, whereas at the logical level we're interested in schemas of both base relations and views or virtual relations. As with many design problems, database design may be performed using two approaches, bottom-up or top-down. The bottom-up design methodology, also called design by synthesis, considers the basic relationships among individual attributes as a starting point and uses those to construct relation schemas. This approach is not very popular in practice because it suffers from the problem of having to collect a large number of binary relationships among attributes as the starting point. For practical situations, it is next to impossible to capture binary relationships among all such pairs of attributes. In contrast, a top-down design methodology, also called design by analysis, starts with a number of groupings of attributes into relations that exist together naturally. For example, on an invoice, a form, or a report. The relations are then analyzed individually and collectively, leading to further decomposition until all desirable properties are met. The theory described in this chapter is applicable to both the top-down and the bottom-up design approaches, but it is more appropriate when used with the top-down approach. Relational database design ultimately produces a set of relations. The goals of the design activity are to preserve all concepts, including attribute types, entity types, and relationship types, as well as generalization and specialization relationships, which are described using a model such as the ER model, and to minimize redundant storage of the same information and reducing the need for multiple updates to maintain consistency across multiple copies of the same information when updates are required. Let me repeat. To minimize redundant storage of the same information. At one university, during the evaluation of a potential new system, it was discovered that as a result of its gradual evolution, the old system had 5 different student tables, making it a nightmare to keep all copies up to date with current information. Before discussing the formal theory of relational database design, we discussed 4 informal guidelines that may be used as measures to determine the quality or goodness of a relation schema design, making sure that the semantics of the attributes is clear in the schema, reducing the redundant information in tuples, reducing the null values in tuples, disallowing the possibility of spurious tuples. These measures are not always independent of one another. Whenever we group attributes to form a relation schema, we assume that attributes belonging to one relation have a certain real-world meaning and a proper interpretation associated with them. They have discussed how a relation can be interpreted as a set of facts. If the conceptual design is done carefully and the mapping procedure is followed systematically, the relational schema design should have a clear meaning. The semantics of a relation refers to its meaning resulting from the interpretation of attribute values in a tuple. In general, the easier it is to explain the semantics of a relation, the better the relation schema design will be. You may remember the company relational database that we designed during the series on ER diagrams. In that one, the meaning of the employee relation schema is quite simple. Each tuple represents an employee with values for the employee's name, e-name, social security number, SSN, birth date, B-date, and address, and the number of the department that the employee works for, D number. The D number attribute is a foreign key that represents an implicit relationship between the employee and department relations. The semantics of the department and project schemas are also straightforward. Each department tuple represents a department entity, and each project tuple represents a project entity. The attribute dmanager SSN of department relates a department to the employee who is its manager, while dnum of project relates a project to its controlling department. Both are foreign key attributes. The ease with which the meaning of a relation's attributes can be explained is an informal measure of how well the relation is designed. Therefore, all the relation schemas in that example may be considered as easy to explain and therefore good from the standpoint of having clear semantics. We can formulate the following informal design guideline. Guideline number 1. Design a relation schema so that it is easy to explain its meaning. Do not combine attributes from multiple entity types and relationship types into a single relation. Intuitively, if a relation schema corresponds to one entity type or one relationship type, it is straightforward to interpret and to explain its meaning. Otherwise, if the relation corresponds to a mixture of multiple entities and relationships, semantic ambiguities will result and the relation cannot be easily explained. Let's look at some examples of violating guideline number 1. The relation schemas in figure 15.3a and 15.3b also have clear semantics. Ignore these lines under the relations for now. They're used to illustrate functional dependency notation that we'll be discussing shortly. A tuple in the employee department relation schema in figure 15.3a represents a single employee, but it includes additional information. The department name of the department for which the employee works, the social security number of the manager of the department. For employee project relation in figure 15.3b, each tuple relates an employee to a project, but it also includes the employee's name and the project's name and the project's location. Although there's nothing wrong logically with these two relations, they violate guideline number 1 by mixing attributes from different real-world entities. Employee department mixes attributes of employees and departments. An employee project mixes attributes of employees and projects and the work zone relationship. Therefore, they violate the above measures of design goodness or design quality. They may be used as views, but they cause problems when used as base relations, as we'll discuss soon. I think that's enough for this video. So this concludes the first video in our series on normalization. And this entire series of lectures is based on a textbook by El-Masri and Navath, Fundamentals of Database Systems, 6th edition. We haven't even mentioned the mystery word, and so since we've been talking about guideline number 1, let's make that our mystery word, guideline number 1. So go ahead and submit your mystery word, and then go out and check your knowledge on the material covered in this video. And when you're ready, come on back to the second video in the series on normalization.